having to wait. So in this case, the GPU, the device is not being used optimally because the device sits idle while you are copying the data. After you have finished the computation, again you have to get the data back to the host. So can we do better still using iCycle? So the answer is yes, we can do better, and the answer might seem pretty obvious. We basically want to be able to do a bit of multitasking, because there's two things that we need to do. One is the computation, the actual computation of entity, and one is the data transfer between the host to device, device to host, both. So what we do is we allocate two buffers in the device, in the GPU. One we'll use for computation, one we'll use for entity, and one we'll use for just purely transferring data to and from host. So the idea is, first you copy the first polynomial in your first buffer, and then you start computing your entity, and while the computation is happening, you basically copy the second polynomial in your second buffer. So you have done nothing fancy, you have just created two different buffers, and while the entity is being computed, you can use the second buffer to copy the data from host to device. And the reason we need to do this is because typically for large sizes of data, the data transfer becomes a bottleneck. It takes longer time to transfer the data between the host and device as compared to the time it takes to do the optimized entity on GPU. So once the entity is computed, finished, entity computation for the first polynomial is finished, now we start the entity computation of the second polynomial, because by the time we did the first entity, second polynomial was being loaded in the device. Now we need to again copy back the result of first polynomial to the host. So we do a simultaneous read and write, where you read the next polynomial in the device and you write back the result of the first polynomial back to the host. Now I know we have an obvious question here, like how do we do this read and write simultaneously, and we'll come to that very soon. But this is basically the idea, where you start entity on one of the polynomials in your device. So one of the buffers in your device is always computing the entity, it's in the compute mode, and one buffer is always in the transfer mode, data transfer mode. And you keep doing that until you have reached the, of course, the last polynomial. Anyone has questions about this particular simple optimization other than this obvious question of how do we do the read and write? So the read and write being simultaneous is actually not factually correct. It's not exactly simultaneous, but there is a way you can do both of these operations in almost the same time. Instead of spending reading and then writing, instead of spending 2x time, you can do it in slightly more than 1x. And the way we can do that is typically when you do data transfer, you need to slice your data into different blocks, and then the data transfer happens blockwise. So for example, let's say in this case we slice the data into 8 blocks. So the data transfer will happen block by block. And now basically what we can do is, let's say you have some new input at the bottom, and you have the device, and the device is done computing the entity. So now we want to write the data from device to the output, and we also simultaneously want to load the new input. So in the first iteration, we just copy the first block from your device to your output, which is your host, which is again your host. The output and new input both are on the host, by the way. And then in the next iteration, you can do a read and write simultaneously, but now it's for different blocks, so therefore you don't have a conflict between blocks. And you can repeat the same process, and you can basically do this operation parallelly. The read operation of the new data and the write operation of the data from device to host. And then you need to do one extra iteration to copy the last block of your new input. So effectively what you spend is 3 cycles in this case, or in any case, if your number of blocks is even 64 or 32, doesn't matter, because you basically do only 3 cycles. So this is slightly more than what you would do. This is slightly more than one whole data transfer sequence of writing from host to device or device to host. So instead of 2x, you are now something like 1.1x or even smaller if your number of blocks increases. So that's how we do pseudo simultaneous read and write in this optimized example in the entity, and we'll take a look at the actual code, actual example of how this works. Questions?
What is the time complexity that can improve after doing this?
So time complexity improvement is almost 3x, because if we go in the naive method, so basically let's assume these 3 are equal. They are not, but let's assume they are equal. So this is like 30 times whatever is that constant. But now in that case, you do 20 times. Sorry, it's not 3x, it's 1.5x, because in that case you reduce this time and this time to just 1, and also both of these things are happening parallelly. So actually it's 3x, my bad. Should be 3x. There's one downside though of this optimal method that I just described. Can anyone point out what's the downside of this optimal method? So we were able to like parallelize the data computation and the data transfer, but then there's a very small cost to this. Yeah, exactly, that's right. So we are using more space. So if in the naive method you are able to do, let's say, 2 power 22 sized entity all at once, now you can only do 2 power 21. The maximum size of your entity becomes half. But that should be reasonable, because the modern GPUs, especially these H100s and then the 4090 from NVIDIA, they have pretty good local memory on the device. So you can do pretty large entities. Cool. So the downside was just that the maximum size of entity you can do is now half. So this is a quick code snippet of how this optimal entity works. We'll actually run both of these examples hands-on, and we'll try to run it all. We'll try to run these examples together. Basically, I wanted to highlight couple of points here. First is, even though Icicle is trying to make things as simple as possible or as easy as possible for developer, but it is not some golden oracle that's just going to solve all your problems. You still need to do some kind of basic optimization, just like we did for the entity. So naive entity is going to take 3 times more longer as compared to this simple optimization. So that's first point. Second point is Icicle allows you to do that in a very simplistic manner. That's what I'm going to describe. So we don't need to go over this entire code, but I'll highlight the main sort of blocks of how Icicle allows you to do these kinds of simple optimizations, but have a big impact. So in this example, of course, you can set the size of your entity, you can set the size of how many entities you want to do. So it's 16 in this case. The next thing is you can define using Icicle different streams for different types of computation. So in this case, you need 3 streams. One is for actually computation, like actual entity computation. One is for host to device data transfer, and one is for device to host data transfer. And this just makes it cleaner in terms of in terms of GPU implementation, so that things are segregated and 2 things don't overlap with each other. So what I wanted to highlight here is Icicle gives you a very simple way to create different streams for doing different types of computation. If you know that you can separate the data and run separate computations, or the data is independent, then you can define multiple streams, which is pretty easy to do. And the last thing that we wanted to highlight here is we saw in the visually the example of how we do the simultaneous computation. You do entity and you do data transfer all at the same time. And the 3 lines that I'm highlighting here, line 73 is where we are doing the entity, and you will see the stream that we use is called config compute. So it's using a different stream, so the entity is being run or computed parallelly to what's happening in the rest part of the GPU. What's happening in the rest part is data transfer. So you'll see lines 77 to 80, we are transferring the result from device to host, and line 83 to 86, we are copying the new input from your host to device. And one thing you'll notice is both of these things are happening parallelly for most of the iterations. Like if you see the condition on line 76 and line 82, it's only the first and the last iteration where only one of these things happen exclusively. But for remaining whatever n-2 iterations, you see that both of these lines of code is going to be executed, which means they are being executed parallelly. So basically what we are doing is this line is doing the data transfer, entity computation, and these lines are doing the data transfer to and fro. Questions? Yes.
Teacher, can you run the example? It's not working. Maybe afterwards we can talk about it.
Okay. Okay. Cool.
Yeah. No.
Yeah, it's okay. We can figure out later. Okay, so this was the entity example, and we'll see. We'll try to run this actually in the Google Colab GPU. There's a couple of slides, roadmap, and then what's kind of like the summary. But I guess we'll do that later when we are closing. So now let's actually get our hands dirty and try to set up, try to actually use for that I'm going to open the instructions. Can you guys see the instructions? Should I make it a bit bigger?
Yeah.
Okay. Now, now, okay, cool. So what I'm demonstrating here is um, a basic like 4-step to installing Icicle, or how you can basically run tests with Icicle. So let's get started. I would request those of who you want to try. Yes.
Is there a link? Can you share?
Yes, there's a link to this. I can share this. How do I share this? I'll create a QR code. I don't generally use Discord. I'm on Discord, but then
Access the access.
sorry.
Yes.
Yeah, sorry. Okay, let me create a quick QR code.
I think spray is small.
Can someone scan it and just share it in Discord? Works? Okay. Okay, I've shared the QR code. Let me know when we should start. Okay, I think let's get started. So first thing you should do is just open a new Google Colab file on whatever Google account you want to use. Then you need to install Rust. We are going to try and run some Rust tests. So therefore we need to install Rust in Google Colab file. So actually I'll do it in a new file just so that everyone can follow. Oh, before that, one thing I forgot to say, which is you need to first connect to a GPU instance. So if you're following the screen, you basically need to click on this change runtime type and use a GPU. So we'll connect, takes few seconds to connect. Okay, it shows that I'm connected. For those of you who are trying, just let me know when you connect to the GPU instance so that we can start. Okay, which step you guys are on? For those of you who are trying. Connected? Okay, now you should install Rust using the first command. If you have installed Rust, just make sure it's installed by just checking the version. The next thing we'll do is just check the configuration of the GPU you are connected to. So if we run these commands, it should give us the summary of what GPU you use. So typically, like, Google provides these smaller and free GPUs. You'll see the memory here somewhere 15360 MBs, which is pretty, like, it's not great, but it's okay as long as we are just running some examples. Okay, the next thing, step one was basically just installing Rust and then checking the GPUs. The next thing we want to do is, so in this particular example, we are just going to simply run a few tests from the original source repository, source icicle repository, and later we'll see how we can run like a different library that we have written somewhere else, but that uses icicle as a library, as an import. So here I'll just copy this. We need to clone the repository. Okay, once the repo is cloned, we need to set up the backend for the repository. By backend, there's a piece of software that you need to fetch if you are using the CUDA backend. So in this case, we are using the NVIDIA GPU. So we need to link our GPU to icicle, or basically let icicle know that here's the GPU. So for that we need to install the backend. So we'll go into icicle, we'll go into the repository that we just created. Then the next step is we'll create this new directory called CUDA backend. You can name it whatever you like. This is the backend directory basically. So the actual CUDA backend that icicle provides, we are going to place it in this directory. Okay, so this is the step where we download the CUDA backend from icicle releases. So this link is from the from our open source icicle repository, and you can see we are downloading the version 3 of the CUDA backend that icicle provides. Any issues? Okay, so we just download this file and extract it in the CUDA backend folder. Okay, the next step is basically the most important, because what you are doing here is basically setting a variable, environment variable, saying where do you find the CUDA backend. So if you run this, it's going to set this environment variable to point to the path where we install the CUDA backend. So typically, if you have your own repository and you want to use icicle, you'll have to do this step where you download the CUDA backend of wherever you want, like in any directory, and then you need to link it so that icicle knows where to find the CUDA backend. Once we are done with this step, we can basically run some tests. So I'll go into, so I'm going into this BN254 wrapper, Rust wrapper inside icicle, but this does not need to be the source repository. Like in this case, it's the source repository, but when you are working with your own